You've seen them, right? Those huge, almost silent giants turning on the horizon. But how do we get from that, from a simple breeze, to the electricity that powers an entire city? Well, that story is one of the coolest engineering puzzles of our time. Let's get into it. So this is the big question, isn't it? On the surface, it seems so basic. Wind pushes a blade, the blade spins, and poof, you've got power. But making that system dependable enough to power millions of homes, day in and day out, that is a whole different ballgame. And this is what that scale looks like in the real world. I mean, just look at that. These aren't just windmills. They are full-blown power plants, engineered to survive storms out at sea, planted deep in the ocean floor, and all connected together in these enormous farms. Okay, so to really get how this machine works, we've got to zoom all the way in, right to the blade itself. And here's the first surprise. Most of us had the basic idea wrong. It's not about the wind pushing the blade. It's about something way more clever. That's it right there, lift. It's the exact same principle that gets a jumbo jet off the runway. The blade is shaped like a wing, so as air flows over it, it has to travel faster over the curved top surface. This creates a pressure difference, a vacuum really, that pulls the blade around. It's not a push, it's a pull, and that pull is so much more powerful. So if lift is the secret sauce, how do you get the most out of it? Well, this chart is basically the recipe. You're looking at a map of efficiency. You've got the speed of the blade tips on the bottom and the angle of the blade, its pitch, on the side. The goal is to live in that dark red zone. That's the sweet spot, where you're squeezing every last drop of energy out of the wind. If you're not in that zone, you're just letting power blow right by you. But here's the catch. Even with the perfect design, you hit a hard wall set by physics itself. It's called Betz's law. Think about it. If a turbine was 100% efficient, it would have to stop the wind completely. And if the wind stops, well, there's no more energy to capture. So the absolute theoretical max is 59.3%. All of that incredible engineering is a fight to get as close to that number as humanly possible. So that's the blade. But a turbine is so much more. It's not just a passive object waiting for the wind. It's a dynamic, thinking machine, a robot, really. From way down on the ground, all you see is the tower, the blades, and this big box at the top, which is called the nacelle. It looks so simple, so peaceful, but inside that box, a high-stakes balancing act is happening every single second. And this is what's going on inside. This is the turbine's brain. Now, I know it looks crazy complicated, but let's just break it down. On the left, you've got all the data coming in, wind speed, rotor speed, you name it. Then, all that info goes through this maze of calculations. And what comes out on the right? Two simple commands: how to angle the blades and how much resistance the generator should create. It's this constant dance between all these factors. So that complex brain is basically always in one of three moods. When the wind is light, its only job is to keep things turning, just to stay in the game. When the wind is perfect, it's in hunting mode, constantly adjusting to stay in that efficiency sweet spot we talked about. But when the wind gets too strong, its job completely flips. It actually starts to spill wind on purpose by changing the blade pitch, protecting itself from damage while keeping the power output perfectly steady. All right, we've gone from the physics of the blade to the brain of the turbine. Now we're going to zoom out one more level. What happens when you put a bunch of these smart machines right next to each other? Well, that's when things get chaotic. This chart shows something most people never think about. Look at the turbine on the far left, number 1. See how high its power output is? It's getting that clean, fresh wind. But now look at turbine 2, and 3, and 4. The power drops off a cliff. What on earth is going on? It's called the wake effect. The first turbine creates a wind shadow behind it, a zone of slower, choppier, just messy air. So for every turbine stuck behind another one, they're dealing with two huge problems. There's less power in the wind for them to capture, and the wind they do get is turbulent and unpredictable. And this chart shows that chaos perfectly. See the violin shape for turbine 1? It's skinny. That means its power output is pretty consistent. But look what happens as you go down the line. The violins get fat and wide. That width means the power is swinging wildly up and down. For the people managing the power grid, that kind of chaotic energy is an absolute nightmare to deal with. Now, it's worth pointing out that all these challenges mainly apply to the giants we're used to seeing, the horizontal axis turbines, or HAWTs. There is a totally different design, the vertical axis, or VAWT. They're usually not as efficient for huge farms, but they have some neat tricks. They don't care which direction the wind is coming from, and they're often simpler, which makes them great for smaller or more specialized jobs. So, we've gone from physics to the machine to the farm. Now for the final zoom out. How does all this theory actually get built in the real world? Let's take a look at Poland as a case study to see the human and financial side of this story. Let's start with the potential. According to projections, by 2040, wind power could add 450 billion Polish zloty to the country's economy. To put that in perspective, we're talking about an injection of around 100 billion euros. This is way more than just an energy project. It's a massive economic opportunity. And this isn't just some fantasy. Just look next door at Germany. When their government created the right policies, the growth was just explosive. Between 1990 and 2013, their wind power capacity went up by more than 56,000%. It just goes to show what's possible when the conditions are right. Of course, building this stuff costs a fortune, and the costs don't stop once they're built. Just keeping them running, service and maintenance can eat up a quarter of the total lifetime cost. Then you've got property taxes going to the local towns, you have to lease the land from farmers, and of course, you have the massive loans you took out just to get the thing started. And this quote from a report back in 2010 really captures that feeling of momentum. Even then, you could see how dynamic the whole sector was becoming. It was clear that wind was about to start playing a really important role. But that potential runs into a wall of real-world problems. For any new project, there's a mountain of hurdles. Just getting a slot to connect to the power grid is a huge challenge. The paperwork and permits can take years, some of the longest in Europe. Local rules about how far a turbine has to be from a house can wipe out 60 or 70% of the land you thought you could use. It's so expensive and risky that no one can do it alone. You need these complex financing deals where investors and banks all share the risk. So, what a journey. We went from the invisible force of lift on a single blade to the complex brain inside the nacelle, to the chaotic dance of a whole farm, and finally to the massive real-world effort it takes to build one. So, after all that, what's next? Because at the end of the day, the real challenge isn't just about building a more efficient turbine. It's about designing a smarter system. One that weaves together the physics, the engineering, the economics, and the politics. It is a giant, fascinating puzzle. And figuring out how to balance all those pieces, power, profit, and the planet, that is the great challenge for all of us. Thanks for joining this explainer.